Hi, today we're going to talk about a really classic problem in fishery management and in general in applied ecologies, that is to estimate population size. We're going to do that in one of the most simple and also classic way. So by using basically a Mark Recapture approach. This is the rationale of how it works. Well, first of all, we have two sampling campaign. We're gonna get out in the field the first time, and let's say that we sample a certain number of individuals. We refer to that as N1. That is the number of individuals captured the first time. We mark them in some way. We put a plastic tag, we number them, and then we release back into the natural environment. We go back a few days later and we sample again a certain number of individuals. Will be likely different from the first one, so let's call it N2. And then we'll look at the animals that we got at, and we'll find that some of them, and we refer of them as M, have been previously captured, marked, and then released, and now recapture. And so we basically want to use this information to estimate population size. If we assume that the population is roughly constant and there are no major sources of mortality, which partially means that the time span between the two sampling campaigns is not too long, and if we assume that it's been random sampling, the behavior of the population is now being of the individuals has now been affected by the tags, the fact that it's been marked, and there is a perfect mixing into the population, then the fraction of previously marked individuals in the second sample should reflect the fraction of individual sample in the first time on the overall unknown population we refer to as N tot. So basically, that is what we're using. The fraction of N1 or N tot should be equal, the same to the fraction of the marked individuals in the second sample. And if that is the case, it follows that we can compute the total number of individuals in the population as the product of N1 and N2 divided by M. Now there is a problem here. The central point in this method is performed by the number M of recapture in the second sample. That is the individual that been already marked in the first sample. If we could repeat the experiment and take another second sample of N2 individuals under identical conditions, we would probably obtain different values of the number we capture. Well, actually, probably get also different numbers, N2, of individuals that are sampled the second time. N2 has a probability distribution that depends on how many individuals there are in the population, N tot, and on the sample size, N1 and N2. We can use a likelihood approach to estimate uncertainty associated with the estimation of the mean population size, the estimation of the mean population size. We will see in a few weeks more formally how it works, but the basic idea here is that we need the probability of obtaining the observed number of recapture for different possible value of the parameter N tot. This problem has been analyzed in a fairly old paper, analytically, as it used to be done by Gacy and Staley in 1986, who kindly provided the probability of recapture in this classic Mark Recapture example, which is reported here, where the terms in parentheses mean, the combinatory, numbers of ways, the numbers of ways we can select M individuals, for instance, from basically N1 individual and a sample of N1. So let L of N, given the number of recaptures, indicate the likelihood of a particular value for N tot, the total number of individuals, given that there were M recaptures. That is the probability of obtaining exactly M individual recapture if N tot equals the hypothesized value of the population. So this is basically the form for the likelihood that here, and it is easier, as we will see, to work with the log likelihood because we can sum up those terms there, and then we can use this information basically to maximize the likelihood, basically, see the data, that we have seen, and in addition to that, compute a 95% confidence interval that includes all the basically values of density whose log likelihood is within basically the chi-square distributions with the 5% significance and 1 degree of freedom, divided by 2, and this basically provide the values of 1.92. Let's look at quickly at an example. It's fairly easy. Assume that we get out the first time and we sample 30 individuals. We mark them all and we release in the environment. A few days later, we come back. We assume that the mortality is negligible, the behaviors of individuals has not been affected, and we sample individuals for reason related to just shear lags or different environmental conditions. We sample more of them, 40, and we find out that 12 of them have been previously captured, marked, and released. And so we have N1, N2, and M. So here we can compute basically the likelihood for them, and we can find basically that the expected number of individuals is 99, and by identifying here the basically intersections between the likelihood functions and the maximum likelihood minus 1.92, we identified basically this interval of points that is between 78 and 142, that is basically the confidence interval for these estimations. And so you can see the method is pretty robust, although the confidence interval is pretty wide, and there are other more sophisticated way to basically approach this problem. Mark Recapture is kind of a branch of science on its own. There are dedicated software in R and other packages that might take advantage, for instance, of multiple events of marking and capturing, marking, releasing several times in order to improve the estimate of the population size in the first place. And they can also be used to provide an estimation of apparent mortality in some cases. We're not going to go in that level of details for time limitations, but there is an R script that is available also among the course material that we can use to run some simulations and see how in practice we can implement it.